Welcome to Chemistry Lesson 5.01, and the title of this is Electrons Motivated to Change, but this is the first video in this packet or in this chapter. So what we're going to do in this chapter is we're going to look at the way, the last chapter was where the electrons are at. In this chapter, we're going to look at the way that electrons influence behavior. So we have talked about the fact that protons over and over are kind of like the name of the element. They're the name of protons are an element's identity. In chapter 3, we talked about the fact that neutrons contribute to mass. So neutrons, and whoops, N-E-U-T-R-O-N-S, neutrons are tied to the atomic mass and isotopes. Well, when it comes to behavior, it's all about electrons. And so electrons have everything to do with an element's behavior, and not just any electrons. We're going to say specifically valence electrons. The inner shell electrons really don't have a whole lot to do with anything, but the valence electrons have everything to do with the way that an element behaves. So to discuss this, let's look at fluorine and let's look at sodium. And I'd like you to pause the video, and I'm going to switch to, I'm just going to stick with green. So we're going to do the orbital diagram notation for fluorine and for sodium. So pause the video and give me the orbital diagram notation for these. All right, hopefully, here we're back. You have 1s, 2s, 2p. And down here for sodium, you have 1s, 2s, 2p, and we have 3s. So if we look at the number of electrons for fluorine, when it's neutral, fluorine has an atomic number of 9. And so filling these with the correct, using Hund's rule and Aufbau, we're going to fill the 1s first, then the 2s. So there's electron 1, 2, 3, 4. Then we go 5, 6, 7, and then we pair them up, 8, 9. So when I fill sodium, sodium has 11. So I'm going to go 1, 2 in the 1s, and then we go 2s. Then the 2p fills first singly, and then it doubles up. And then I have 1 electron in the 3s. Well, these are both main group elements, and that matters. So these guys are main group. And a while back, we said the thing about main group elements is they're governed by a law. Main group elements and non-main group elements have different, way back when we talked about the periodic table, we said that if you're a main group element, it's a little bit like living in America, where you have a speed limit of 70 and a drinking age of 21. You're a non-main group element, so the intertransition metals and the rare earth metals, it's like living in Germany, where the drinking age is 18 and there's no speed limit on the Autobahn. There are more rules. There's more regulated behavior for the main group, and that main rule is called the Octet Rule. And what the Octet Rule tells us is that all main group elements, try to achieve or try to obtain 8 valence electrons. Why do they do this? Well, it's because it's the lowest possible energy state, and we know that elements like low energy. That's the reason why when we elevate electrons to orbitals, they don't like to stay there. They want to fall back. And so the reason for this is because it is the lowest energy state. Kind of like how when you have a day off, you don't want to, most of you don't want to run around and clean your room and walk the dog and do the dishes. You want to lay on the couch and watch Netflix. preferably with a group of friends, eating Cheetos and not thinking about what you're going to eat. So we have the same thing here. Now remember, inner shell electrons, let me switch to red. So these are my valence electrons for fluorine, because the valence electrons are the highest energy level, and the highest energy level here is the second. So this guy has 7 valence electrons. And by the way, I'm going to be abbreviating valence electrons a lot, VE. So how many valence electrons does sodium have? Well, yeah. So this has 1 valence electron. Well, these are both main group, and so they want to get to 8. Well, how does that work? Well, fluorine, it's pretty simple to see. It's got a vacancy here. And so if it can bring an electron in, it'll have 8 valence electrons. And often this is what, actually all the time, this is what fluorine does. So to get 8, it has to gain an electron. Well, this guy, sodium, only has 1 valence electron, and gaining 7 valence electrons is just not feasible. There's a much easier way. Do you see what it is? Yeah, all he's got to do is kick this guy out like he's a 40-year-old living in the basement without a job. Hit the road, Jack. And if we get rid of this, now our valence electrons are here. So if you get rid of this top one, that leaves these 8 beautiful valence electrons. So by losing an electron, we have 8. And it's this tendency to gain or lose electrons that leads to properties among the elements. It also gives rise to what we learned in chapter 3, are elements with a charge, which we call ions. So let's go back over that now. An ion is an atom with a charge due to a change in electrons. So what we have when we have fluorine, so I'm going to do when fluorine, and that's just capital F, gains an electron, and it only ever gains 1 because that satisfies the octet rule. We have 9 protons, but now we have 10 electrons. So this is going to be positive 9. This is going to be negative 10. This gives me a negative 1 charge. When sodium loses an electron, that gives me 11 protons, because my protons don't change. That gives me 10 electrons, and that's going to give me a +1 charge. Why? Because positive 11 and negative 10. So remember, this always has a positive charge. This always has a negative charge. Well, here's the thing. Fluorine, chlorine, bromine, iodine, and astatine all have, even though it's in different levels, they all have their valence electrons, so all of the halogens have an S2P5. Now the numbers in front change. So fluorine is 2S2, 2P5. Chlorine is 3S2, 3P5. Bromine is 3S2, 3P5. But they all have this basic configuration. So that means that all the halogens are going to gain an electron, and all the halogens are going to have a -1 charge because their valence electron arrangement is the same. So if we look at sodium and potassium and all of the alkaline metals, so if we look at the alkaline metals, they all have an S1 designation. Now sodium is 3S1, potassium is 4S1, rubidium is 5S1, but they all lose an electron in order to meet the octet rule. And when you do that, you end up with a +1 charge. So not only can we know about the ionic charge of an element based on the column that its main group is in, we can also know about how it behaves, because valence electrons lead to behavior. Because the halogens all have the same valence structure, they have the same behavior. Because alkali metals all have the same valence structure, they all have the same behavior. And we're going to look at some of these properties, at some of these behaviors. The next one, reactivity, we're going to do in class. So we're going to jump from 501 to 503, because we're going to do 502 in class. So with that in mind, take a look at magnesium and tell me, what is the ion that magnesium is always going to form, and how do you know that? So let me write that practice question out. And let's go with purple. Let's do a practice question. What charge will the alkaline earth metals, what charge will the alkaline earth metal ions always have, and why? All right, go ahead, pause the video, and answer is, we'll do the answer in a second. So the answer is that all of the alkaline earth metals, so if we look at beryllium, beryllium's going to be 2s2 for its valence. Magnesium's going to be 3s2. They're all going to have an s2 as their top, as their valence electrons. So these are their valence electrons. So in order to get a full octet, they're going to lose 2 electrons. And if you lose 2 electrons, that's always going to give you a +2 charge. And when you're back in class, look at the upper right corner of all the blocks on the alkali metals, and you'll notice that it says +1. If you look at the upper right on the alkaline earth metals, you'll notice it says +2. If you look at the column next to the halogens, which is oxygen and sulfur, you'll notice that it says -2. Well, why is that? They have 6 valence electrons, so if they gain 2, it's going to give them an octet and a -2 charge. So this tendency to want to achieve this leads to these behavior patterns, and that's the topic of our packet, our chapter, is behavior patterns on the table and behavior patterns in bonding. So we'll start off with bonding with the main group, but then we'll talk about what happens with the transition metals, and the rare earth metals. All right, so that is a quick intro to why electrons in the main group, remember this is only main group, so our takeaways here, these are main group elements trying to follow the octet rule. All their behaviors tied to their valence electrons, and they're trying to get those 8. The magic number is 8. So they will either gain or lose accordingly, and then as a result, the groups or families have tendencies in their behavior. Okay, that's all for now. Have a good day.